All right. Good morning, everyone. Assalamu alaikum. Thank you, Fatma, for the invitation. So, my name is Salman Khan. I'm a faculty member in Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi. My main area of research is computer vision, machine learning, and we have been specifically looking into the application of recent generative AI models for Earth observation and remote sensing applications. So in today's talk, I would like to go over a series of works we have done. And the essence of it, the connecting element here is around how we can take this vast amount of Earth observation data, which is available in petabytes, and can connect it with automated tools enabled through artificial intelligence that can analyze and understand that data for us because this is not manually possible. This is the main highlight of today's talk. And I would like to start with a few text-only models and a few multimodal models that can process both images as well as textual inputs. Right. If we look at the current landscape for remote sensing image analysis, we see that several of the existing models that you find in even available solutions, the commercial solutions, they're very, very task specific. So you will have one sort of machine learning model that can do classification, for example, in SAR imagery, another model that can be used for multispectral or temporal sequence analysis. And similarly, for high resolution imagery, there are separate models for aerial imagery and so on. So this is, of course, very, very task specific. And the bottleneck there is then we don't have general purpose tools that can analyze all sort of data, which is available in the rich data sources that our satellites have been gathering. This is one of the current limitations. The second thing is that we need to be an expert typically to interact with the Earth observation and remote sensing data. And the motivation we have here is to see how we can connect with the generative AI advancements. So you all might have heard about ChatGPT, Gemini, Claude models from Anthropic, which can talk to you. So basically, you can ask any query, you can ask a question in a natural language of your choice, and these models try to understand your query and then generate a response that satisfies your question. The goal here is to see how we can connect this vast amount of Earth observation data, which we have available, with the automated AI tools together with the conversational capabilities. So we can enable these models to answer intelligent questions based on the analysis of this Earth observation data for us. So the current limitations we find in these general purpose tools is that, first of all, they are generic tools. So recently, initially when these models were there, they only can process textual inputs, but recently many of these models can also accept images and videos as inputs. But still, they have generic knowledge, so they do not understand the specific classes, land use classes, for example, types of change, types of disasters, which are commonly observed in Earth observation and remote sensing imagery. They also cannot process multispectral input, for example, SAR image inputs, and similarly temporal inputs to detect, for example, changes and so on. So there are certain limitations in terms of their core capabilities. But another challenge is also they are hidden behind the API walls. So basically, we cannot understand on which data these models are trained on, what are the inherent biases or rules that these models use for making certain decisions. Because eventually, if we want to put any of these models in production, anyone would like to understand exactly of what kind of data and rules have been used to train these models. So our goal here is to develop open source technology using generative AI models, which can connect this vast amount of Earth observation data with the natural conversation capabilities. So as a starting point, we started with only a text-only model, and this was developed in collaboration with Core 42, which is a G42 company, and this was showcased in COP28. And this is a first bilingual a large language model, which is dedicatedly trained for climate intelligence. So this model can take in queries in English and Arabic to basically cater the need for Arabic speaking world. So as we know, there are close to 400 million Arabic speakers. And the goal here is to see how we can build on the open source tools, for example, JACE model, which is a generic Arabic LLM, and Vicuna and Llama series of English models to have a specific model, dedicated for climate intelligence, which can answer intelligent questions about any of the climate and sustainability related topics. Then we use specifically, factual data in the training of this model so that we can ground our responses in factuality, and we can provide references for any of the key facts we present through this model. But we believe that this could be a really good educational tool because many people have misconceptions about climate change, sustainability. They have questions about, how they can perhaps improve their certain practices to minimize, for example, waste, and just a little bit lifestyle improvement can lead to certain benefits. So all of that we wanted to target through this domain-specific large language model. So how we trained this, we accumulated a lot of different available public sources of data, for example, Climate Bench, which has climate question answers, but then we appended it with additional sources, for example, factual data from the CSC data sets and CCMRC. So these are all available publicly data sources, and we converted that into conversation style instruction sets because eventually we want the model to have this conversational ability and instruction following ability. So if a human asks it to, for example, write one paragraph about a certain sustainability topic, then it can comply with that instruction. So in order to do that, we need to do a training with the large scale data. And in this instance, we collected roughly 1.4 million instructions, which incorporate UAE context and have specific information about the COP28 event. For example, what are the main events which are happening and on which day and so on. So all of this information was fed to the model in training so that it can generate intelligent responses. So this was one of the starting points. And as I mentioned, this is just a language model. So our goal was to see, as I mentioned initially, how we can go beyond just the textual inputs and perhaps connect also the multi-modal inputs like images and diverse set of other sensory inputs that we encounter in remote sensing imagery. So for that purpose, we had our first conversational multimodal model, GeoChat, which is an intelligent Earth observation model. And as I explained during the motivation, the motivation here was to combine a lot of these scattered individual tasks. So this single model was trained to not only do scene classification, so it can, given an image, it can classify it into one of the land use classes, for example, but it can also generate a description of the image, which we call as image captioning. If you provide it a particular region, so for example, if I give it this red, a bounding box around a house, then it can explain that particular region as well. And as you can see in these examples, and similarly, any generic visual question answers, it is able to answer generic questions about the visual imagery, which is input to this model. And similarly, we wanted to have these localization abilities as well, because many times there are a number of visual elements available in a high resolution imagery. So a lot of houses, for example, in a urban landscape, many parks, buildings, resorts, and so on. So we wanted to also have this ability of grounding. And by visual grounding, I mean the model should be able to locate where a particular object is. So if you look at this example, this grounded image captioning example, if we ask this assistant to describe the image in detail, it will generate this description, for example, for this kind of an input image. So the image depicts a scene with, for example, multiple buildings and houses and trees. But these colors basically show that the model is also localizing all of those individual objects or group of objects in the input image. So for example, when it says 10 tennis courts, then it can point me to the rough location of these 10 tennis courts in the input image. So this we call as the visual grounding task, and this was the first model which could do visual grounding in the literature. So this paper was published in IEEE CVPR last year, which is the flagship conference in computer vision. Right. And as I explained initially in the motivation, the goal here is to see how we can perhaps connect the non-expert users, people who do not are necessarily experts in remote sensing domain, but they know how to speak language, of course, and they can ask any intelligent question from this model, and the model should be able to understand that and respond appropriately given an input modality. So this was the starting point, and then recently we have extended this in collaboration with our partners at IBM, and this model is also hosted under UNDP Sustainability for Development Initiative, and we have extended this model to not only take in RGB inputs like color image input, like the one I showed in the previous example, but we extended it to also intake SAR imagery from Sentinel-1, for example, and also multispectral input, for example, from Sentinel-2 satellites, and also multi-temporal inputs, which mean before and after change images, for example, to locate and localize specifically where the changes have happened, what kind of changes are there, if there is a long series of temporal sequence, what is a trend of evolution of a certain change. So, for example, perhaps damage due to fires and how that area is getting recovered over a long sequence of images. So the model can also provide outputs which are localized. So this I indicate with the segmented outputs. And we carefully wanted to have a lightweight and efficient design. So I will talk about it a little bit in the next few slides. But the main essence is that we are intentionally trying to have a lightweight model so that it can be hosted on a single GPU card and it can be served easily through multiple instances for any queries and the deployment time. So this is basically the essence. And for this purpose, we actually had to gather a huge amount of data from all the available sources and then clean and refine that over different iterations. And eventually we ended up with roughly 22 million image and question answer pairs. Out of that, we preferred using 11 million more, you can say, refined or correct label sets for training this model. And then we evaluate it on 40 different downstream tasks. And of course, the goal was to actually be very, very comprehensive, as I explained initially, and cover all these different applications ranging from, for example, tree species classification to detecting methane plumes and what is their extent, how much emissions that can be observed through satellite imagery. If there is any reforestation happening, so that can be also analyzed. And similarly, we analyze the urban heat island phenomena, like, what changes can be done to the landscape. We could also do object detection, as I mentioned, and damage assessment and detection due to, for example, different natural disasters, earthquake, flood, and so on. And one remark I should mention here is that because this is the first research effort, so there are still several failure cases we encounter, and we have been iteratively trying to actually improve our data pipeline and retrain the model again to see how we can further improve it. But for this purpose, we also present a new benchmark, which I will be explaining in the upcoming slides. So this is mainly about the applications, but there are several other applications as well, which we covered. As I explained earlier, we are kind of evaluating this model on nearly 40 different data sets which are existing in the literature. So a little bit about the model architecture. This is for the new version, the latest version of our model design. We call this Earth Dial from Earth Dialogue because basically what we are trying to do here is to have a dialogue with the Earth observation data. So I know this is a bit more technical, so I will try to simplify it as much as I can. So if you can see here, this pink box here, this is a simple large language model, but now it can accept different inputs, multimodal inputs. And by multimodality, I mean, any of these inputs. So for example, RGB images, as I was mentioning, thermal bands, infrared imagery coupled with RGB, synthetic aperture radar inputs, multispectral, and then multitemporal inputs as well. And then we have a kind of a fusion mechanism. And what in essence it is doing is it is trying to fuse information and make it more compact so that the LLM can operate on it and understand what is happening in this visual imagery. And then we have the textual inputs, and they are tokenized and they are also fed to the same LLM. And eventually, if you look at the top kind of row, here are all the list of different tasks for which we are training this model. So the more important things here in this architecture is, of course, the LLM. And in this case, we have been using the Phi 3 LLM, which is from the Microsoft, and it is a very strong LLM in the small language model domain. And we couple it with a visual backbone, which is called Intern V80. This has 300 million parameters, and this Phi 3 mini model has roughly 3.8 billion parameters. Um, so this visual encoder is actually distilled from a much larger vision encoder, which originally had 6 billion parameters, but then for efficiency reasons, but also optimizing for performance, this small scale model is distilled from the large scale model, but then it can also perform similarly to the 6 billion model. So these are the two main components, the vision encoder here, the multimodal LLM, and then how we are fusing and combining this information. So this is a quick overview of architecture, but then how we train this model. So we have different stages of training. So we start with a little bit of pre-training with large scale data, but the data quality is slightly, you can say inferior in this case, because in order to optimize for large scale, we had to compromise on the quality of the annotations which are available in the first stage, but we do a relatively large scale pre-training on different modalities, both high and low resolution data sets, and we train everything. So including the LLM, the multi-layer perceptron, which act as a connector, connecting the vision transformer backbone with the LLM. And then in the next stage, we do a little bit of fine tuning using LoRa. So LoRa is actually a parameter efficient fine tuning mechanism, which basically the goal here is to not disrupt the original training, which is done in the pre-training phase. And then we share these weights in the third stage. And in the third stage, we introduce additional modalities like multispectral and SAR inputs. And if you see here, going from left to right, this is kind of a progressive learning. So we are teaching the model more and more difficult tasks as it goes in, and looks at more amount of data. So we start with just in a consistent format. And then we introduce the additional modalities like SAR and multispectral. So a little bit about, what is our data composition for all these stages. So as I mentioned initially, we have high resolution, low resolution, multispectral SAR, and thermal as well as temporal sequences. But then we introduce this in this fashion. So if you look at the stage one, we have data sources from NAIP, Sentinel-2, Landsat, and SkyScript. So these are the existing data sets. And we use specific formats for the token. So basically, what this means is that whenever I append a nape image, for example, I will append it with this particular token format, which means high resolution RGB image at this resolution of 0.5 meter, right? And this acts as a mechanism for the model to figure out what kind of questions we might expect on top of this input imagery. So for example, if we are doing change detection in stage 2, I will append this kind of token which says change detect and then high resolution RGB temporal with this particular resolution. And then the model can understand that maybe the question that a user will ask will be around change detection or monitoring changes across different temporal instances of the images which are provided. So this acts as a mechanism to handle multiple tasks with a single unified model. All right, so I will move on to some examples from this model. So if you look at these examples, we are depicting many different tasks that this model can achieve. So as you can see on the right-hand side, there's an image with some cars, some tennis courts, and some roads and infrastructure. And then we can ask any questions about this. So for example, we can say for multi-label scene classification, we can say classify the image, and these are the different options you should choose from. And then the model will choose from these options to provide, for example, there is a tennis court, parking, and vehicle present in this image. And similarly, we can do, if we want to do visual grounding, as I mentioned, the model can give me bounding box coordinates, and we are showing these coordinates on these images. So if you can see here, these blue boxes are coordinates are given in this answer, which is depicted over here. But I can also do, more specific tasks. So I can say, for example, referring expression. So I can say, give me the location of the tennis court at the center, and the model will give me the three bounding box location, just to simplify the exact location of a particular object. Then, so these were all examples for the RGB domain. We can also process multispectral inputs, and here are a few examples. So for example, if you have an infrared image, which is of course from an aerial platform, and we can ask any questions. So for example, describe the object in this bounding box. So I can provide this red bounding box, and I can say, okay, what does it look like to the AI? And then the model says one person located at the bottom. And this is the output from the model. Similarly, we can ask it to describe the image in detail, and it can say, okay, it's a satellite on an aerial image. So I think this is an incorrect response, as you can see, because the model has been trained on huge amount of satellite data, so that it says satellite data, but actually this is perhaps aerial image. There is one person, and it gives me the coordinate, and located at the bottom, one person located at the top right, and it can also do, for example, counting for these instances. Similarly, on the right-hand side, you can see a SAR imagery, and in synthetic aperture radar, I'm asking about, for example, what is the location of an object, what type of object is there, can you describe the image in detail? It will try to not only explain that in text, but also it tries to locate that in the visual inputs which are provided as to the model. So a few other examples for example, change detection. So we can give bitemporal images before a disaster and after a disaster, and we can say what kind of changes you observe. And in this case, this is not specifically a disaster image, but it's just like at different time instances. So in this case, there are new roads which have been built along this time, and the model actually talking about that from just the SAR input. So in this case, we are just doing change detection with SAR inputs, but we can also, of course, do with RGB inputs, as is shown in the bottom left example. With multi-temporal change detection, we are providing 4 examples images, and we are asking the model to summarize what kind of changes it observes. It will say, okay, some roads have appeared and some buildings have been constructed, and then we can continue the dialogue from there. Similarly, we can ask about, for example, whether there are, in terms of the forestation, deforestation, are the vegetation in growing? Is it like, healthy? Are the rates of vegetation going up or down across a time period? So again, a few more examples. We can also pass it with multi spectral inputs, combining RGB with magic band outputs, which track methane. And we train the model to actually not only give a location of the plume, but also, talk about the extent to which this plume is observed. And similarly, we can do, for example, the counting of, so if you look at, for example, this right query, it's kind of a complex query. So how many large ships are present at the harbor in the center? So the model has to understand what is the harbor, what are ships, and then what are large ships. And then what is the central harbor in this image, and it generates this response which is approximately correct. So if you look at the central harbor, you will observe that approximately there are 9 large cruise ships which are docked there. All right, so we can, of course, use it for many different downstream applications. A few applications I will go through, but of course, I believe being the domain expert, you will have much better ideas than me. So we can use it for infrastructure localization for monitoring purposes. We can talk about the road transport management. So, for example, in this image, the model can talk about a dense traffic cluster, and it can probably figure out the congestion on the road and so on. It can also do, for example, management of water transport. So how many ships are there, where they are docked, and is there a harbor nearby, and so on and so forth. But the more interesting applications we observed were, sort of some of the out of the domain images we used to test our model. And this is a relatively older version of the model that we use for testing. So in this case, we are providing two images, one from 1984 of Cairo City, and second one roughly 40 years later in 2022. And I'm saying, okay, can you compare these two satellite images and then describe how the model has expanded in last 40 years? And then, it talks about, for example, how the river data has kind of narrowed down, and what kind of urbanization and development has been done, of course, in generic terms. But then if we have specific data that can be fed to the model for training, then it can also generate more specific outputs, on a more localized area as well. So I would like to then show another interesting use case. This is a slightly disintegrated from the conversational platform, but our goal is to actually eventually connect all these different layers of information with the same conversational capability. So in this case, we are comparing before and after images from Sentinel-2, which are publicly freely available at 10-meter resolution. So before the rain in Dubai in the April last year, and after the rain images. So we took both these images, we compared what are the changes which have happened, and then so you can see perhaps like, a lot of these water pockets appearing in blue on this image. And then we try to see what kind of analysis we can do, through this data fusion. So we pull up a lot of these labels from OSM, so OpenStreetMaps, and we try to see, okay, how many buildings or schools and areas have been affected. So if there is a bit large water pocket, is it close to, for example, maybe a hospital or maybe a school, and educational facility, or cafe or restaurant, and so on. And we identified, like, how much infrastructure is also potentially damaged. So in this case, we estimate, like, roughly 4.7 impacted roads, percent roads were impacted. And if, like, total number of roads were close to 3,000 kilometers, roughly 140 kilometers were affected. Of course, this data is pulled up all from open source sources, so this may not be complete, but this is, like, coming from the open kind of annotations, these which are crowdsourced from OSM platform. Right, so I will next like to show another use case we have been working on for the Abu Dhabi city, and this is mainly centered around urban heat islands. So previously I showed you a few examples in which we have integrated the urban heat islands with the conversational model GeoChat and Earth Dial. But in this particular analysis, we just look at, the decade of data for Abu Dhabi, trying to understand how the temperatures have been changing and through smart interventions, how we can control the temperature. So again, this was done in collaboration with IBM. We have a center of excellence on our campus in Abu Dhabi. And this model is also one of the models which is hosted at UNDP platform for AI for sustainability development. So basically here, the goal is to see how AI models can be used to identify urban heat islands, study how they are impacting people, and potentially pinpoint the factors which are contributing to urban heat islands, and also maybe analyze and provide mitigation measures that can help bring these temperatures down. So, just to define what do we exactly mean by urban heat islands, as we know, the metropolitan areas can be excessively hot in the summer. And this is, I mean, a phenomena which is observed most commonly in EU and North America. What we observe in Abu Dhabi is actually the opposite. So the urban areas are slightly cooler in UAE, Abu Dhabi, and Dubai in comparison to, for example, the desert environment, of course, because of the vegetation, as I will explain later. So what kind of data we use? So we pull up data from Landsat and Sentinel-2, and we are basically using the harmonized version of where, like, both images are available. And this kind of satellite crossing is done right in the morning. So we have these images, observed close to 7 a.m. Early in the morning. And what we do here for Abu Dhabi is to pinpoint five key areas, and some of these areas are metropolitan areas with high-rise buildings, like Medina Zayed area and Al Reem with high-rise buildings, a few low-rise building areas like Al Mushrif, and then one industrial area, Musaffa, which is, like, at the bottom, and then Masjid City, where our campus is located, which is again a low-rise building close to the airport. And we look at a number of information variables here. So we get the Landsat maps, which provide us the infrared band together with RGB. We combine it with what are the population density information, what is the climate, kind of climate classifications we can do here. And um, and what I mean, where are the high-rise buildings, where are the low-rise buildings, and so on. That classification segmentation we do here, and we also combine it with how many buildings are present here, so that we can estimate population density and so on. And with this, we compare 10 years of data. So this is a map for 2014, and we average, these temperatures over a month, so that we can have more reliable statistics. And we also get this developed area affected. So of course, this is also pulled from the classification of land use and the OSM, and the density is actually obtained from the density of points in the OSM again. And the DAA, we observe, like, the developed area affected, like how many buildings actually are getting very close to the very hot points. So this is the basically one measure we have. And we are also comparing the mean temperatures, whether they are growing over the 10 years or not. So if I jump 10 years ahead in 2023, we observed that typically, if you compare both these images, typically the mean temperatures have been rising. And of course, this is not, so these are just observed from the satellite sources and is averaged across a month. And these are not validated with the ground station data so far. But we can see the trend. So, for example, we observed that a lot of, area where a lot of development has happened, like Al Reem Island, we see a big, kind of jump in temperatures, and the developed area affected is also grown. And similarly, for areas like, which are industrial, like Musaffa, there is a big kind of rise in temperatures again because of perhaps the emissions and the lack of vegetation as well. So how we can mitigate those? We look at certain parks which have been developed in the last 10 years to understand how much they are contributing to bringing down the temperatures. And of course, this is not, I mean, an citywide temperature decrease. It is just a localized temperature decrease we observe from the satellite imagery. And in this case, we observed that, for example, the Masdar Park, which was non-existing in 2019, once it was built up, it kind of helped in bringing down the temperatures for the whole month, approximately 1 degree Celsius cooling effect overall for the same time period observations across the month. And similarly, for parks which were already there, but the amount of vegetation was increased, like Imarat Park in Mushrif area, there we observed a slightly less cooling effect, but of course, this is quite significant, I mean, in comparison to the other areas where the vegetation has been decreased, or for example, a lot of construction has happened where the temperatures were actually rising in this period. So we were also very much interested in understanding how we can account for the carbon sequestration potential of our cities. And for that purpose, we developed an object detector that can detect all the trees for Abu Dhabi. And through that, we wanted to estimate, like, what is the carbon sequestration potential for our cities? Because as you know, trees act as the natural sink for carbon, and they are a very valuable resource for sustainability, with our growing cities. So we counted all the trees on Abu Dhabi Island, the area which I'm showing here in the black kind of polygon. And we estimated that roughly the carbon dioxide sequestration potential to be close to, 63,000 tons. And then, of course, because this is an automated analysis, so we can use that to track over a period of time as well. All right, so with this, I would like to conclude. I started with the climate, JS Climate, which is just a text-based model for conversations on climate and sustainability-related topics. And then we transitioned into the GeoChat and Earth Dialogue models that can basically process like multispectral and multi-temporal, multi-resolution inputs and can answer intelligent questions about those modalities. So we contributed a large scale data, as I explained, with a few examples. And we have observed some interesting results on zero shot and supervised applications. And as I mentioned, we have been actively trying to see what are the gaps which are existing in the current vision language models, where they fail, what are the difficult challenges, and there are a number of challenges. So, for example, these models can hallucinate, they can, sometimes they can misinterpret the instruction, and this is an active research field which will greatly benefit. I mean, if there are more stakeholders involved, and if the data sets can be extended, and I mean, more further effort in terms of both the core architectural design and the improvement of data set is put in place. So with this, I would like to summarize, and if there are any questions, please feel free to ask.